335 meters of vertical rock and concrete. That is the height of the Rogun hydropower plant, a structure taller than the Eiffel Tower, holding back the Vox River in Tajikistan. This is not just a dam, it is a loaded weapon of potential energy. 13 cubic kilometers of water are pressing against a wall built in one of the most seismically active zones on Earth. The risk calculation is terrifying. A single structural failure here releases a kinetic force capable of wiping out everything downstream for hundreds of kilometers. But the real engineering miracle isn't the height, it is the invisible seam holding this leviathan together. How do you stabilize a megastructure on a foundation that is actively trying to slide apart? The answer lies in a complex system buried deep within the core, designed to counter the shifting tectonic plates. The salt layer beneath the dam is dissolving. The secret seam mentioned earlier is actually a massive nervous system. Every layer of this artificial mountain is wired with thousands of geotechnical sensors. Above ground, the Vox River Valley is disappearing under a man-made peak. Heavy compactors grind rock into place, creating a vibration you feel in your teeth. They are raising the Earth 335 meters into the sky. But deep beneath this crushing weight, the logic flips. While the surface team piles millions of tons of rock, the underground team is removing it. They are carving out hollows the size of Gothic cathedrals directly under the rising dam. It is a structural nightmare. The mountain pushes down, tectonic stress pushes sideways. The sensors monitor hydrostatic pressure to ensure the machine hull doesn't implode under the burden of the dam itself. Engineering becomes a battle against claustrophobia. Massive turbine components must be dragged through narrow logistical throats. In the humid dark, crews work in shifts that blur together, pumping high-density concrete into the steel mesh. The machine hall caverns must survive the crushing weight of the mountain above. But these diversion tunnels face a different, more violent enemy: speed. At full discharge capacity, water does not flow. It tears through the rock like a liquid saw. This is the physics of cavitation. As velocity spikes, pressure drops, creating millions of vacuum bubbles that collapse against the tunnel walls. The sound is not a splash, but a continuous, deafening explosion. This force eats standard concrete like sugar. To survive stage 4, engineers cannot rely on simple thickness. They install a secondary lining, a high-strength armor reinforced with silica fume and steel fibers designed to withstand this relentless bombardment. But the armor is useless if the skeleton crumbles. The surrounding rock is riddled with microscopic fractures. Crews drive injectors deep into the stone, pumping cement grout at pressures exceeding 1,000 pounds per square inch. The mixture hunts down every fissure, solidifying the mountain into a single, watertight monolith. The pumps stop. The pressure holds. Deep beneath the surface, there is only absolute silence. In the mountains, engineers fought to reinforce solid rock, but beneath a modern metropolis, the enemy changes state. Here, the ground is a treacherous soup of water and soil. To dig here is to risk a catastrophic sinkhole that could swallow skyscrapers. The solution is not a shovel, but a pressurized vessel, the tunnel boring machine. This is a subterranean factory with a diameter of 14 meters. That is the height of a 5-story apartment block buried underground. The mechanics rely on a critical balance of pressure. As the massive cutter head rotates, the machine pumps a pressurized bentonite slurry into the excavation face. This viscous liquid pushes back against the earth, holding the tunnel open while the steel teeth grind the soil. Inside the operator's cabin, the atmosphere is sterile, air-conditioned silence. Screens monitor torque and hydraulic pressure with clinical precision. Yet just inches away, on the other side of the pressure bulkhead, is a chaotic storm of crushing mud and grinding stone. The machine swallows the debris, mixing it with the slurry and pumping it to the surface in a closed loop. Above ground, a treatment plant separates the solid waste from the bentonite, cleaning the fluid and sending it back down to the fight. Behind the shield, the machine builds its own protection. Hydraulic arms lift massive precast concrete segments. They lock together to form a waterproof ring. The TBM pushes off these new walls to drive itself forward. Once the first tube is complete, the machine does not surface. In a specialized underground cavern, the entire assembly performs a massive U-turn to bore the twin tunnel back to the start. The city above never feels a vibration. To keep this underground giant fed requires a logistical army moving 3,000 tons of supplies every 24 hours. We emerge from the subterranean depths, but the physical stress does not vanish. It simply changes form. Here on the surface, gravity relentlessly attacks machinery weighing 300 tons. These 7-meter-tall titans rely on advanced diesel-electric propulsion systems to conquer steep gradients. But the real enemy is friction. In this landscape of dust and raw torque, logistics becomes a war against thermal breakdown. Engineers must calculate road angles with surgical precision to minimize stress on the drivetrain. A single miscalculation destroys the profit margin. The tires alone represent a critical economic risk. Just one of these rubber colossuses costs 40,000 euros. Losing a set is a €250,000 disaster. The engine roars, the hydraulics hiss, and the massive bed tilts backward to release its burden for the next phase. We move millions of tons of rock to build dams, but sometimes nature beats concrete. February 2017, Oroville, California. The main spillway fractures under the force of record snowmelt. The sound is deafening, a roar of water tearing through reinforced steel like paper, shaking the valley floor. 188,000 residents are ordered to evacuate instantly. The timeline is brutal. Engineers have just months before the next wet season to demolish and rebuild 900 meters of the concrete chute. The slope is 4-to-1, too steep for standard paving. Crews work around the clock, using winched rollers and structural concrete to armor the scar. Speed is the only metric that matters. That was crisis management. 6 years later in Colorado, the Gross Dam project proves that precision prevents panic. Here, the goal is expansion. Engineers are raising the dam's crest by 33 meters, effectively adding a 10-story building on top of the existing wall. The challenge is the joint. If the new concrete does not fuse perfectly with the old, the pressure will shear it off. GPS-guided bulldozers spread roller-compacted concrete in layers exactly 30 centimeters thick, 12 inches, 0 deviation. The structure rises vertically at a pace of 30 centimeters a day. The fresh material chemically cures into the old foundation, turning two distinct eras of construction into one seamless monolith. But the water is already waiting to test the seal. On the surface, dams can collapse, so it is safer to descend to the bottom of the Baltic Sea. The Fehmarnbelt project ignores traditional tunneling. Instead of boring through the earth, engineers assemble the tunnel underwater, piece by piece. In a custom-built factory, crews cast 89 hollow concrete elements. Each segment spans 217 meters. The weight is staggering, 73,000 tons. That is the mass of a fully loaded aircraft carrier. Yet the plan relies on them floating like corks. Workers seal the open ends with steel bulkheads. Then they flood the dry dock. Archimedes' principle takes over. The water displaces the mass, and the concrete leviathans lift off the floor. Tugs drag the structure into the open ocean. The placement requires surgical steady hands. Ballast tanks flood, initiating a slow descent into a trench dredged 40 meters below. Sensors guide the drop. The margin for error is just 12 millimeters. Then comes the lock. As the new segment touches the previous one, high-powered pumps evacuate the water between the bulkheads. Thud, a vacuum shock. The immense hydrostatic pressure of the Baltic Sea instantly crushes the two elements together. The massive dual rubber gaskets compress, fusing the concrete blocks into a single watertight artery. Outside, the currents rage. Inside, there is only dry, heavy silence. Underwater, the threat is crushing pressure, but above the waves, the enemy becomes wind and fatal imbalance. The Zuari Bridge in India rises using the balanced cantilever method. It is a high-stakes balancing act. Construction moves outward from the central pylon in perfect lockstep. One segment added to the left requires an identical counterweight to the right. A single timing error creates a catastrophic lever arm. The pylon snaps. Gravity wins. Steel cables represent the only defense. Inside high-density polyethylene ducts, galvanized strands are threaded and tensioned by hydraulic jacks. The contrast is absolute. Slender cables suspend thousands of tons of reinforced concrete. The jacks apply force with millimetric precision, lifting the deck to its exact calculated profile. But the air itself attacks the system. Wind and rain induce vibrations that cause metal fatigue over time. Engineers install dampers near the anchors to kill the resonance. The steel survives. Tension is conquered, but will the ground itself hold? Infrastructure demands sacrifice, but sometimes physics itself forbids construction. We are at 4,500 meters above sea level. This is half the cruising altitude of a commercial airliner. Here, the air is not just thin, it is hostile. A standard diesel engine operates on a precise mixture of fuel and oxygen. When the intake valve opens at this altitude, the cylinder fills with void instead of air. Inside the combustion chamber, the fuel injector sprays a fine mist, but the oxygen count is too low to burn it all. The result is immediate asphyxiation. Thick black smoke erupts from the exhaust pipe. The engine sound changes from a steady roar to a ragged, suffocating cough. Power output drops by 40%. A 50-ton excavator suddenly performs like a 30-ton weakling. Engineers must reprogram the turbochargers to spin at critical speeds, forcing the machine to operate in a state of chronic mechanical anemia. The contrast is brutal. While the steel giants gasp for air, the human operators inside face the same hypoxia. Medical stations and oxygen masks are as essential as fuel. Yet the mountain must be tamed. Workers hang from ropes over 500-meter drops to drive steel anchors 9 meters deep into the granite, literally stitching the unstable slopes together. To carve the road without collapsing the peak, the team initiates pre-splitting, where a precise line of charges detonates milliseconds before the main blast. If in the Andes the enemy is air, in Valencia the enemy became gravity and the decay of concrete. The Estadio Ciudad de Valencia was built in 1968. Its original skeleton is brittle, and adding a modern roof creates a parasitic load, dead weight that the 50-year-old column simply cannot survive. The solution does not rest on the building, it hovers above it. Engineers installed a massive steel compression ring around the entire perimeter. It weighs 1,040 tons. That is the equivalent of 20 battle tanks suspended over the stands. This ring operates on the bicycle wheel principle. The outer steel rim resists the crushing force, while a web of high-strength cables pulls inward, holding 17,000 square meters of membrane taut. The old concrete supports nothing. The new structure floats on pure physics. Intelligent tension is stronger than massive concrete. But even perfectly built structures start dying the second they are commissioned. Example, the main artery of the world. The Suez Canal fights a permanent battle against sedimentation. Nature is constantly trying to close the wound. To keep the channel breathing, operators deploy the Almira Cutter suction dredger. Mobilization is a logistical sprint. The team must load the massive unit onto a heavy transport vessel in a strict window of 2 hours. Draft calculations allow zero margin for error. On the water, the process turns violent. The rotating cutter head grinds against the seabed, chewing through compacted silt to guarantee passage for deep draft supertankers. This decay is global. In Denver, the threat is underground erosion. Teams are rapidly ripping out disintegrating lead lines to install corrosion-resistant pipes. We fight to hold our ground. The desert watches. While we patch the Suez, in the heart of the Sahara, engineers decided to rewrite the laws of nature from scratch. The Great Sand Sea does not forgive mistakes. Here, the sun strips moisture from the air in seconds, and the ground drinks any spill instantly. To force a river across 114 kilometers of this furnace, Egypt had to build a hermetically sealed artery. The engineering relies on a precision gradient invisible to the naked eye, 1 inch of drop for every 100 feet of distance. This specific angle allows gravity to pull the water forward without the turbulence that leads to evaporation. But the sand is still the enemy. To stop the dunes from absorbing the supply, the canal wears armor. Excavators carve the trench into the bedrock. Teams unroll miles of black, high-density polyethylene sheets. Concrete panels lock the plastic in place. It is a waterproof skin, isolating the precious flow from the arid ground. At the El Hammam station, the pumps roar. They drive millions of cubic meters of treated water into the wasteland, turning dust into circular fields of green. This is not just irrigation, it is the physical modification of a continent. The cost of terraforming this hostile void exceeds 9 billion euros. From the thin air of the Andes to the new rivers of Egypt, this was a chronicle of overcoming. We analyzed the friction between human ambition and planetary physics. Turbines fighting for oxygen at 30,000 feet, steel structures bearing parasitic loads, the relentless silt of the Suez. These are not just construction sites, they are front lines. To reveal the invisible forces at play, we fused raw documentary archives with predictive AI models. Neural networks visualize the stress fractures and hydraulic pressures that no camera lens can record. We showed you the mechanics behind the concrete, the anatomy of the impossible. But entropy is patient. Every structure has a breaking point. Which of these engineering colossi is destined to fail first? The desert pipeline or the high-altitude engine? Leave your technical verdict in the comments below. For the next investigation into the machinery that runs our world, confirm your subscription now.